Hello everyone. So see, in today's class we will see applications of thermal conductivity. So first one, cooking utensils are made up of copper and aluminium. Why? Because they have more thermal conductivity. In winter, metal chair is colder to touch than a wooden chair at the same temperature. Stainless steel cooking pans are referred with extra copper bottom. Why? Because coefficient of thermal conductivity of copper is greater than coefficient of thermal conductivity of steel. Cooking utensils are provided with wooden handles, and woolen clothes keep us warm in winter. So these are what applications of thermal conductivity. Put down. Let's move ahead. And now next part is convection. What is convection first of all? As already we have seen, it is a process by which heat flows from the region of higher temperature to the region of lower temperature by the actual movement of the particles of the medium. For example, land and sea bridges, yes, during daytime, land is hot, water is cool. So heat flows from land to sea, that is called land bridges. Whereas in night time, air flows from water to land or sea to land, that is called sea bridges. This is what convection. Now next to difference between natural and forced convection. So first point, you see natural convection and forced convection. In natural convection means what? Transfer of heat due to the movement of fluid resulting from difference in density. Means hot air, cool air. Hot air will have less density, cool air will have more density. On that, or that density will decide the flow, we can say. That is what natural convection. In forced convection, transfer of heat due to forced movement of the fluid by mechanical means such as a fan or pump. Means basically exhaust fan, something like that. Next you see, in natural convection takes heat from bottom to top, whereas in forced convection may take heat in any direction. Let's see one more example of this. So natural convection example is sea and land bridges, and forced convection is what? Exhaust fans. Understood? Note down. So let's move ahead. Now see, heat is transferred from the wall to the fluid by a combination of conduction through the film and convection in the fluid. The rate at which heat is transferred by convection is P, which is equal to Q by T, which is equal to HA into delta theta. Where what is A? A is what? Area of the wall. Delta theta, temperature difference. H is what? Convection coefficient. What is this convection coefficient? The rate of heat flow due to convection when a fluid moves along the surface of a body of unit area with unit temperature difference between the surface and fluid. For example, you see here, just the formula I have changed. H is equal to P by A into delta theta, and its SI unit is watt per meter square into Kelvin. I'm just keeping like this: watt meter power minus 2, Kelvin power minus. Okay. So let's move ahead. And now radiation. What is radiation first of all? See, the process of transmission of heat from one place to another place without the necessity of the material medium. This already we have discussed in beginning only. See, for example, sunlight, it does not require any material medium for transmission. Yes. Now, intensity of heat at a point is directly proportional to 1 by r square, or inverse proportional to r square, where r is what? The distance of point from source. more the distance, less will be the intensity. Okay, got it? Next one. Now, types of substances. So how many types of substances are there? Ditherminous and atherminous substances. First one, in ditherminous substance, a substance which allows heat radiations to pass through it without absorbing them. So it will not absorb, just it will allow to pass. Whereas atherminous means what? Which partly absorbs. Okay, while transferring, it will absorb some amount of heat. In ditherminous substance, for example, dry air, SO2, rock salt, and here wood, metal, moisture. These are the examples of atherminous substance. Okay. So let's move ahead. Prevost theory of heat exchange. Now, what is this Prevost theory of heat exchange? Every body emits thermal radiation at all temperatures above absolute zero and exchanges heat energy with surrounding. That is, the body supplies heat to surrounding and in turn receives heat from them. So meaning is what? Any body above absolute zero will emit some radiation first of all. Okay. So this is what Prevost theory. Now reflectance, absorptance, and transmittance. You see this diagram here. This Q is what amount of heat incident. This is some amount which is radiated, some amount absorbed, and some is transmitted. So see here, Q is amount of thermal energy incident, R is reflected, A is absorbed, and T is transmitted. So if we will add these three, that is reflected, absorbed, and transmitted, you will get the total amount of thermal energy incident. Now what I am doing, I am dividing throughout by Q. So R by Q plus A by Q plus T by Q, this is Q by Q, which is equal to 1. And this R by Q is nothing but what? Reflectance, or you can say reflecting power. This A by Q is nothing but absorptance or absorbing power, and this T by Q is nothing but transmittance or transmitting power. And these all are just ratios, so they don't have any unit. Okay, note down. So see now, just before on before page we have seen R plus A plus T is equal to 1. Now for any specific wavelength, R of lambda plus A of lambda plus T of lambda is always equal to 1. Emissive power or emittance. So what is emissive power? For particular wavelength, that is monochromatic, we can say energy per unit area per unit time into wavelength. This is what? Emissive power or emittance. And that's why total emittance, if you want, you can just take integration from 0 to E, or 0 to infinity for E lambda d lambda, or 0 to E for d. So energies for all wavelengths, we can say. Okay, this is what? Total emittance. Next, what is emissivity? Emissivity is denoted by small e, and it is equal to E by EB. What is this E? Total emissive power, and EB is what? Total emissive power of black body at same temperature. That is called emissivity. Okay. So let's move ahead. Spectral absorptive power. Energy flux absorbed by the body in certain time. Energy flux absorbed by the body in certain time divided by energy flux incident on the body in same time is called spectral absorptive power. But what is this energy flux? Energy flux is nothing but power. Okay, energy emitted per second, we can say. That is what energy flux. So this spectral absorptive power means flux absorbed divided by total flux incident, we can say, or energy flux incident on the body. This is just a ratio. Okay, next one, total absorptive power. This is denoted by A, and it is just integration from 0 to infinity of A lambda d lambda. Whatever you got, this A lambda or whatever the wavelengths you have, you just take summation of that, you will get total absorptive power. Next one, Wien's displacement law. This law or this question on this, you will get question of 2 marks, particularly in IP. Even in problem also, they may ask on this concept. The wavelength lambda m corresponding to maximum radiations is inverse proportional to absolute temperature of the black body. So lambda m is inverse proportional to T, and that implies lambda m into T is equal to constant. Okay, lambda m into T is always equal to constant, and this constant is denoted by B and called Wien's constant, and its value is 2.89 into 10 to the power minus 3 meter Kelvin. Okay, right? So note down. Let's stop here.